Okay, hi everyone, Happy New Year. So this is Xiaofu. So I have both the background from mechanical engineering and also electrical engineering. So my current affiliation is I'm working as a full-time employee at a large tech company. And at the same time, me and also my PhD supervisor, we also have a tech startup company. And our company are mainly study the nonlinear system, nonlinear dynamics. And we utilize this nonlinear system on a lot of different applications, such as computers, uh, energy harvester, biomimetic robots. So if you are interested, you can take a look at the website. So I list the website link and also the QR code you can scan. So in whichever way you choose, it should direct you to the same position. So if you're interested, do take a look. Right now, back to our main topic. Today, my main topic, I'm going to teach you how you can communicate correctly or efficiently between two different FPAAs. And along the way, when we are doing one quick example, I will teach you some quick tips. So those are very, I would say, kind of important. It can actually really save you a lot of FPA capacity and also time. So this is how our example is going to look like for today's tutorial. So right now, let's take a look at how the final version look like. This is the final version. We are going to start a new one. So let's go to File, New. Right now, you have a brand new one. So drag FPA1 to the middle. So you can, so it looks like it is small, so you can zoom in or zoom out. I would like to zoom in a bit so that it looks much better. So right now, what you can do, so we'll take a look at our slide. It tells us A equals to 2 plus 1 times 0.5. So we'll do 2 plus 1 first. So how can we get 2 plus 1? In FPAA, you have a specific CAM. CAM stands for Configurable Analog Module. So what you can do, scroll down a bit. So we have half cycle, sum, difference. We can also use it to sum or subtract one another from another. Okay, right now it tells you, okay, it doesn't really like your clock frequency clock A, that's your clock A, larger than 2 megahertz. What you can do, let's say we reduce it. How can we reduce it? Okay, good question. We can reduce it if you double click. We have the setup. So clock A is picked from clock 0. Instead of using 4 kilohertz, let's use a much smaller value. We use 1000 kilohertz. Sorry, my bad. Let's say whether it solved the problem. Okay, you see the warning error just gone. So you have to click OK, otherwise the question mark will be 0 all the time. Let's say, okay, we are good, or we agree on our current setup. Let's click OK. The question mark will just go away. And how can you get constant value from FPAA? Good question. So go back to insert new CAM. We will use DC voltage source at the almost very bottom. So you can see some of them said yes, right? And some of them said no. No means these are not Anadigm approved modules. If you use them, they might give you incorrect or inaccurate results. So when you are looking at those CAM, so make sure they are Anadigm approved. If I just set approved, that means Anadigm approved. So the one we used are fine. They are Anadigm approved. Okay, we need to get 2 plus 1, right? Okay, 2 plus 1, let's say we can use 2 DC sources, copy this one, and you get a new one. You don't have to go back to insert new CAM to find another, to find the same DC voltage source. And here you can also rename it to different name. So if you don't like N1 and N2, and in the future, if you come back to take a look what you are trying to do in this simulator model, if they don't labeling correctly, you are confused. Let's call it DC1 means DC input 1. Another one we'll call it DC2. Okay, right now we have 2 plus 1, right? And you might be thinking, okay, we have 2 plus 1 and we have to multiply it by 0.5. Then you were thinking, okay, let's just have a multiplier. Let's just make things more complicated. We have a multiplier. Okay, you put multiplier here. It sometimes errors out because your clock frequency doesn't match. So okay, we will make it match. We choose clock B at a different frequency. Right now, you can say, okay, it errors out because it doesn't really like it to be more than 4 megahertz. But that's something you will do it in later tutorial. I'm not going to show it for this one. But the main point I would like to show is that, okay, you have 2 plus 1, you have to multiply by 0.5. Then you need to use a multiplier. While you don't have to do it that, difficult or that complicated, just factor this out. So you have 2 times 0.5, you have 1 volt. 1 plus 0.5, you have 0.5 volt. So basically, if you can make your input from 2 inputs from this cam as 1 and 0.5 volts, then you don't have to use this multiplier, right? You can also save some capacity for this FPAA. I will do this simple way. Delete the multiplier. Okay, how can you make your this DC voltage source? They only have 2 options, either +2 or -2. We choose +2 volts. So how can you make it 0.5? How can you make it 1 volt? Okay, very simple. They have scaling factor for each one of the input. So the upper one, I would like to make it from 2 volts to 1 volt. I will multiply by half. The lower one, still the input is 2 volts, but the scaling factor will become 1/4. So you have 1 volt and 0.5 volt. Okay, right now you have your first step done. So we get our A. Then I would like to do the rest of the computation in a different FPAA. Right now, right click and insert new chip. Our chip is using AN231E04. So find the same name and insert it. Okay, right now you have 2. Then, okay, I need to use one of FPA 1 as output. Let's say I would like to use 1718 as output. Double click and go to output. It's just trying to ask whether you are using input or output mode. Since we need to output the signal, we choose output mode. For right now, you will choose bypass. So you might be wondering what are single-ended or VMR. VMR, this one, so itself is basically is I would say a constant voltage represents for 1.5 volts. So in FPA or Anadigm company, they generally will make your 2 differential input signal or output signal centering about 1.5 volts instead of 0 volts. That's just your internal design. So we don't have I would say any solutions to change it. Let's just agree with for bypass for right now. Alright, so then for FPA2, for sure you will need 1 input, right? Since we have output, we also need input. Let's say we will use this terminal or this port. Since right now it's off, we'll turn it on. So it's asking you whether you need input or output mode. We'll use input mode. Same thing for bypass. We don't use any other, I would say, advanced functions for right now. Okay, after you choose bypass, okay, you were wondering, okay, you have 17, 18, and is 17 go to 1 or 2? Okay, let's go back to our, let's go to the datasheet. So datasheet, you go to page 19. First column means pin number from the simulator. Second column is the actual terminal or ports from the circuit board. If you go to 1718, it tells you, let's say this is 1718. It tells you, okay, IO6P, P means plus. IO6N, N means negative. So if you check the name, it said that input output SIO6. Let's go back to our simulator and double click. you see this instant name, they are fixed. You are not able to change it. If you change it, that means you wouldn't be able to recognize it. So same name, right? In IO 6. Well, it'd be very interesting stuff is that, okay, a bit different from, I mean, if you take a look at 17, 18, they only have, let's say, one set, they only have 2 terminals. While the other one at FPAA 2, they have 4 different terminals. The reason is because terminals, they have separate input-output ports. So if you choose output, they will switch to a different number, 3 and 4. If you use input, they are switching back. The thing is that, okay, those input and output style themselves can be used both as input and output port, but you cannot use them at the same time as input and also output at the same time. That's the only difference. And then, okay, you were wondering, okay, 17, 18, 17 go to 1 or 2. Let's make sure they match. So 17 means plus, right? IO6P. P means positive or plus. And 1 also means P, right? That means plus go to plus. You shouldn't have any sign mismatch. If you don't make 1 plus go to plus, instead you make plus go to minus, then that means eventually you will have a 180-degree phase shift signal. So in order to avoid this phase shift, but sometimes you can also specifically introduce 180 degrees phase shift, since it's basically give you -1 as a scaling factor. So from go back to our simulator, from 17 we go to 1 and 18 goes to 2. Not that difficult, right? And let's call it A plus. And the other one we call A minus. Okay, right now I will give one more sample and hold, so that my signal, when it is going out, is giving us a continuous signal. You don't really have to if your phase matches, but I prefer to add a sample and hold here for 2 different purposes. The first purpose is that it can give us a continuous signal, so it's valid at both phases. So you see this one is only valid at phase 1, the output. Whenever it goes past this sample and hold, you see the output, it doesn't show any phi1 or phi2 sign here. Is because it's valid for both phases. Similar to the DC voltage source, if there isn't any, I would say, labels showing phi1 or phi2, that just means in default it's valid for all the phases or for both phases. Okay, since we are done with A, we are going to get B. B means A subtract by 0.5. We will use still the same one. So let's copy and paste it here. Okay, 2 more things I have to mention. One, since you are having a new FPAA, right now let's take a look at your old one. Your old one, you have clock frequency 0 and 1 at 1000 kilohertz and 16,000 kilohertz. Make sure FPAA 2 also use the same. If you don't use the same, they have clock frequency mismatch. Then you will have different, maybe delay signal mismatch. I would highly recommend you should make them the same frequency. After you make the same frequency, you see the question mark also just die away. So let's say right now that's our A, and we have B, right? B means you have to subtract by a constant. So constant, let's still use a constant voltage source. Drag it a bit far. So, okay, we need 0.5 volts, right? One way you can do it from here, you can choose your input 2 from non-inverting to inverting. And since we are not doing any scaling, for the first input is A, we'll just put 1. For the second one, as our input it is 2 volts, right? So we need to make it 0.5 volt. So we'll temp, okay, correct, it's 0.25. We get 0.5 volt from 2 volts. All right, then we have, basically we have B. And how we can get C? C is fairly easy. So it just need to add 1 volt to B, right? So what we can do here in our simulator, we simply turn on one more input. It in total can turn on 4 different inputs, but depends on what you are trying to do here. It might run out of the, I would say, the capacity for this cam. So, but right now it seems like we can still turn on one more input. We'll use non-inverting as we are trying to add 1 volt to based on our example. So still, what we can do, we can still use the same constant voltage, but we just need to change the scaling factor. So make sure the input is right now 1 volt. Okay, right now we are just one step behind our final goal. So let's say what is our final goal? Final goal means, okay, you need to get C divided by 2. How we can get C divided by 2? There is a specific cam in simulator. So what they can do is that they can get the division between 2 different signals. So close to the very top, you have divider. Choose the divider. Okay, it says that, okay, clock B must be 16, so means must be 16 times. Let's say clock B right now is the same frequency. Let's use a different one. Okay, right now they have the same thing. Okay, but then it errors out, tells you it doesn't really like the clock B at a frequency greater than 4 megahertz. Let's further reduce it. Okay, fine. But if you don't reduce it, it's just a warning error. Let's see what will happen. Right now, what you can do, so let's connect Phi1 to Phi1. And we need to have a voltage, right? So that voltage says that divided by 2 volts. So we have 2 volts here. Let's go back and check which input corresponds to which. Okay, if you go to the documentation and quickly scroll down, it said that V out equals to Vx divided by Vy. Vy is something like a quantized. So quantized, let's go back to the very top. It tells you divided by 8-bit quantized bottom input voltage Y. So Y is basically should be 2 volts. If Y needs to be 2 volts, that means I'm just doing it wrong. So that means this should go to the bottom and this shouldn't. Okay, it errors out. Let's see what it tells you. It said that phase mismatch. Okay, I guess this one has better to be a valid phase for both. So what you can do, you can use input X and sample and hold it so that it actually solves the phase mismatch problem. Let's say what we have right now. So from here, we have C divided by 2. And go back to our documentation. C divided by 2. So that's our C. C is the 1. Yeah, that's Vx. So 2 should be the 1 on the bottom. The divided by the 8-bit. Okay, I just double check we are doing the right thing. Okay, that seems to be correct. Then what you can do from here, go to simulate, set up simulation. Oh, before that, we also need a probe. From here, create oscilloscope probe. Let's add it. one. Let's add one here. As the I will say the output is a bit weird since it's only valid on phase one. I would like to have a much better output, so I will use a sample and hold, and to get a continuous output that is valid for both phase. Okay, let's add one more oscilloscope probe. Put it here. Let's see what was happening. Let's set up our simulation. 5 milliseconds should be good enough. Let's check it. Simulate. Simulation is still running. Give it a bit time. Oh, it seems like, all right, it's taking quite long. Let's further reduce it. Let's reduce the amount of time it uses. But I believe for right now, even we don't further reduce it, it's already good enough, right? So let's use a cursor. And you see the green one, our oscilloscope is reading the entire output. They are supposed to be 1 volt, right? So look at our example. It tells you the output should also be 1 volt. Great, we get the final results correct. So why I have another pink one? I would like to show you, so just recall from my previous tutorials. So phase 1 is only valid for a single phase. That means one clock frequency, or one clock period equals to the amount of time phase 1 takes plus the amount of time phase 2 takes. So that means if you compare the green output and also the pink output, so basically the pink one from our expectation, half of it should be 1 volt, another half should be 0, since they are invalid at phase 2. Let's see what was happening. Let's zoom it a bit. Okay, let's say the green one and the pink one both 1, right? And at the next phase, green one is 1 still, but pink one is 0, which corresponds to our hypothesis or expectation. Okay, in my next tutorial, so I would like to show some more basics or some other math operations. And if you are interested in my Anadigm FPAA simulator tutorial, you can subscribe to my channel and leave comments. I will try to solve your question in my next tutorial. And thanks for watching.